You know that formula for the area of a circle, the one we all had to memorize in school? It kind of feels like this magic spell we're just told to accept. Well, today, we're not just going to accept it. We're going to treat it like a secret code, and we are absolutely going to crack it. So let's just jump right in. If I asked you, right now, how do you find the area of a circle? What's the first thing that pops into your head? I bet for most of us, it's a very specific and, yeah, a very famous formula.
Yep, that's the one. Area equals pi r squared. We all know it, we see it, we use it, we plug in the numbers and get an answer. But that just tells us what to do. It doesn't tell us the really interesting part.
And that is the real mystery, isn't it? Why pi? Why is the radius squared of all things? Where in the world did this elegant little equation actually come from? Well, that's what we're going to uncover.
Okay, so our investigation is going to start with a simple clue. We're going to try to get a rough idea of the circle's area using a shape we all understand really well, a simple square. But first, we just need to make sure we're on the same page with a couple of key terms.
First up, the radius, which we usually just call r. It's super simple. It's just the distance from the dead center of the circle straight out to its edge. And trust me, this is a crucial piece of our puzzle. And the second term is the diameter, or d. That's the full distance all the way across the circle, but it has to go right through the center point. And here's the key. It's always, always exactly 2 times the radius.
All right, got those? Good. Now, picture this in your head. Let's take our circle and draw a square that fits perfectly around it, so it's just kissing the edges on all 4 sides. This means the length of one side of our square is the exact same as the circle's diameter. Now, here's where it gets pretty interesting. Just by eyeballing it, you can tell the circle takes up a big chunk of that square, right? But not the whole thing. Well, it turns out it's roughly 3/4 of the square's total area. That's a surprisingly close first guess.
And what's amazing is how close that guess really is. The actual mathematical ratio is pi to 4. And since pi is about 3.14, well, that is super close to 3 out of 4. So this method gets us in the ballpark, for sure. But it's still just an estimate. To get the real proof, we're going to have to get a little more creative. And this, my friends, is where the real breakthrough happens. Forget about boxing this circle in from the outside. We're going to go inside. We're going to slice it up and see what secrets it's hiding. So the big idea here is to cut the circle into slices, just like you would with a pizza. In math, we call these sectors. And remember, we're not throwing anything away. We're just rearranging the pieces. Now watch what happens. We take just 4 of these slices and line them up, flipping every other one. It's not a perfect shape yet, but you can kind of see something new starting to take form, can't you?
Okay, but now check this out. What if we use 12 slices instead of 4 and do the same thing? See how the top and bottom edges are getting a lot less curvy? The more slices we make, the straighter those lines get, and the more our new shape starts to look like something very familiar. And that familiar shape is a parallelogram. Now just imagine if we could cut the circle into a bajillion, practically infinite number of tiny, tiny slices. Those bumpy edges would smooth out completely, and we'd be left with a perfect parallelogram. So this is the key moment. We've basically shape-shifted our circle into something that looks exactly like a parallelogram. And if we want to find its area, which is the same as the circle's area, remember, we just need to figure out its base and its height. To do that, we need one last piece of info from our original circle, the circumference. That's just the fancy word for the distance all the way around the outside edge. And its formula is 2 times pi times the radius. Just tuck that away for 1 second. Okay, let's put it all together. Take a look at our new parallelogram. What's its height? Well, it's just the length of one of those slices, which is the circle's radius, r. Easy enough. Now, what about the base along the bottom? Well, that's made up of the curved edges from half of our slices, so its length is exactly half of the circle's total circumference. Okay, this is it. We have all the pieces of the puzzle. We took the circle, we rearranged it, and we figured out the dimensions of the new shape using parts from the original one. It is time for the final reveal. And here's the most important principle to remember. Because all we did was rearrange the pieces, the area hasn't changed one bit.
the area of our new parallelogram is exactly the same as the area of our original circle.
And the great thing is, finding the area of a parallelogram is super easy. It's just its base multiplied by its height. So all we have to do now is substitute in the values we just figured out from our circle.
Okay, let's walk through this. We start with base times height. Then we substitute in our circle parts. That's half the circumference for the base and the radius for the height. Next, we replace circumference with its own formula, 2 pi r. Now look at this. The half and the 2 cancel each other out perfectly, which leaves us with pi times r times another r. And that simplifies to our final answer.
And there it is. A equals pi r squared. See? It's not magic at all. It's just a logical result of slicing up a shape and seeing it in a completely new way. The code is cracked.
So let's just recap the big idea here. The secret to the circle's area formula is that the circle can be cleverly rearranged into a parallelogram. The height of that new shape is just the circle's original radius, its base is half the circle's circumference, and when you multiply that base and height together, bam, the familiar formula just elegantly appears. You know, this just goes to show that some of the most famous rules in math aren't just things to be blindly memorized. They're actually the final chapter of a really cool logical story. It makes you wonder, doesn't it? What other formulas that we just take for granted are really just a clever transformation waiting to be unfolded?